Let's try. Hello. Built-in microphone. Okay, awesome. Okay. All right, so next week we're going to do a really cool lab where you guys are going to be able to tell from an instrument whether something is more dilute or more concentrated. Here I can look at these pictures and you can tell which one is more concentrated and which one's more dilute, right? You see how all the volume of all the solutions are the same? Okay? All right, so far so good. We'll start from easy and go to harder. So there's this thing called a solution, and it is a mixture of two things. A solution is a mixture, okay? The lesser amount is what we call the solute. In this case, the solute was Kool-Aid. One of the great learning tools that you guys can do in your life is to have an example in your head of what you're learning. If you will think of Kool-Aid, when you think of the word solution, you'll never forget solute and solvent. Okay? The solvent is the water. The solvent is the water. And I think of this W, how it's further down in the alphabet than with that V, and so I think of solvent and water, and that helps me. Right? So far, so good. So, guys, we're chemists. So we are trying to think of the chemistry of this. So I want you to imagine you're looking at this beaker of Kool-Aid, and you're looking at the molecules of the Kool-Aid. Okay, like you've got X-ray vision, you're looking at the molecules of the Kool-Aid. In a more concentrated solution, you're going to have more molecules of Kool-Aid than you would in a dilute solution. Do you guys see that the volume of the solute right there is not the point, doesn't matter, right? So what we need to do as chemists is we need to figure out a way to measure concentration, and molarity is one of those ways. Molarity is one of those ways. Here are all the different ways that I can use to measure concentration. One of the things I could have done is I could have masked the amount of Kool-Aid that I put in per volume of solution. That's one way I could measure the concentration. Another thing that I could have done is I could have measured the moles of Kool-Aid. Now, am I going to count 6.02 times 10 to the 23? No. What I would do is I would figure out the chemical formula for Kool-Aid, calculate the molar mass, and then mass the Kool-Aid, and then figure out the molar mass. I would do a mole conversion problem to figure out moles per liter. I could do parts per million. Okay, so this toy that you guys love is a way of envisioning concentration. I could say this is this is 1 in a million thing. You guys have seen this, right? There's a million little tiny beads in here, and one of them is black. So I could measure this concentration. I could say, well, there is 3 parts Kool-Aid for every 1 part water. And I could also do percent composition. But in chemistry, this is our main guy. Our main guy is going to be molarity. So this is what you're going to need to memorize. Molarity is a way of measuring concentration. It is the moles of the solute divided by the liters of the solution. Okay? So it is the number of moles of Kool-Aid per volume of solution. If I have a high molarity, that means it's very concentrated. If I have a low molarity, that means it's very dilute. Everybody cool so far? All right, so now we're going to play a little bit with the sim. All right, so you gotta love the PhET simulation. All right, so here's the drink mix. All right, and if I were to add, so I want you guys to look over here where it says molarity. Okay, if I were to add more solute, what is going to happen to my concentration? it's going to go up, and so is my molarity, right? Another way that I could do that is I could decrease or increase the volume. If I increase the volume, look what's going to happen. What happened to my molarity?
It went down.
It went down, and you guys know this. You told me if I wanted to make this more concentrated, what would I have to do?
Add more power.
What would I have to do with the water? Take it out. In other words, I'd have to evaporate it, right? So if I had less, look at my molarity. You see that going up? You see how I made it more concentrated, right?
And the drink's getting lighter.
And the drink is getting lighter or darker. That's correct. So let's don't do Kool-Aid. Let's do something more chemistry-y, like, what would I call this? Cobalt 2 nitrate. That is correct. Cobalt 2 nitrate. All right? Same kind of thing. If I want to make it more concentrated, if I want to increase the molarity, I'm going to add more solute. If I wanted to increase the molarity, I could also decrease the solvent. Hello. Maybe too many things. Oh, there it is. So one of the things that I want to show you is there a way that we could add so much Kool-Aid? Can you guys stop talking, please? Is there a way that we could add so much Kool-Aid that we could actually have Kool-Aid start to pile up in the beaker?
Yes.
Yes. So,
That's my dream.
come on, people. Here we go. All right. So, what would I call this stuff? No. Cobalt 2 chloride. CO's cobalt. Okay? All right? Now, watch this. When I add, for this particular solution, if I keep adding solute, my molarity goes up. Let me add this down a little bit, make it really, really concentrated. Do you see where it says saturated?
Yes.
And do you see what's starting to appear there?
Yes.
This is actually crystals of the cobalt 2 chloride. I made this solution so concentrated that the actual solid starts to precipitate in crystals in the bottom of it. It would be like when you were a little kid, you know, you take a glass of iced tea or something, you want to put sugar in, and you keep putting sugar and sugar and sugar, and you stir it up and stir it up, but at a certain point, does it make sense to you? There's only so much sugar you could add that would actually dissolve. So this is called a saturated solution. If you add too much or take away enough water, you can actually make a saturated solution. All right. So I was laughing the other day because I was talking to one of my students in the other class, and he's like, I said, how's chemistry going? How's it going for you? He's like, it's such a disappointment. He said, chemistry is just a bunch of math. It's like math class. And I hate to tell you, but that's kind of true. All right? Chemistry is math. So we're going to be doing molarity problems here. All right? So you got your pencil ready to go here. What is this is the easiest kind of molarity problem I can give you. What is the molarity of a solution if you have 2 liters of solution and 0.35 moles of sodium chloride? This is the easiest one we have, all right? Molarity equals moles divided by the volume of solution. Do I have both those things? Yes. And so I would take 0.35 moles and I will divide it by 2 liters. Now here's the kicker. The moles have to be in moles, And the liters, the volume must be in liters. All right, so can you divide 0.35 divided by 2? 0.175, okay. Now, this is importante, folks. You can put a capital M here, but what you have to remember is that that is a double unit. You know, like miles per hour, like density in grams per milliliter? This is a double volume in disguise. It really means, not grams, sorry, moles divided by liters. So keep that in mind, okay? It really is a double unit. This is a factor labeling problem. If you want a double unit, you start with a double unit. That's just about as easy as you can get with molarity problems. Let's try a little harder.
So,
Go ahead.
the sodium chloride, that has nothing to do with the equation, like we're never going to look at
Love you. Not right now in this form because I gave it to you in moles. Okay, but you were anticipating what I'm going to do next. Here we go next. What is the molarity of the solution if you have 2 liters of it and 0.35 grams of sodium chloride? Do you want a double unit? Do you want a double unit? Yes, you want moles. This is going to drive me crazy. Per liter. You want moles per liter. So I have to start with the double unit. Do I have moles? No, this time I have grams. But I'm going to start with that because I know I can convert. So 0.35 grams. And what can I put on the volume? Do I have liters? Do I have liters in the problem? Yes. So 2 liters goes on the bottom. Now I know how to convert. So sodium chloride. Here comes my nomenclature. How do I write the formula for sodium chloride? NaCl. Okay? Is there a way that you know of, I know I want to get to moles, in 1 mole of sodium chloride, how much does 1 mole of sodium chloride weigh?
58.5 Gs.
58.5 Gs. How did she get that?
I did the math.
So what did you add?
I added 23 plus 35.
Right, so she added the molar mass of sodium and the molar mass of chlorine. Now do you see how my grams cancel? I'm at moles. Am I done?
No.
Let's look. Do I have moles per liter?
Yeah.
Yeah, so I'm done. Yeah, that was an easy one too. All right, so math girl, calculator girl, 0.35 divided by 2 divided by 58.5. 0.0029. Right. Well, how many sig figs do I have though?
Oh, you have
2.
3.
Nope.
One.
1. I only have 1 sig fig, and so 3 times 10 to the minus 3 molar. Okay? Or you could say moles per liter. Either way.
Would we label it like big M and then NaCl? Or do we not have to have that?
You don't have to have that for this particular one. I mean, that would be great. That would be good. All right? Yeah. What is the molarity of a solution if you have 2 milliliters of that solution? 0.35 moles. But what do I have to do now with my volume? Stay with me. I got to convert it to liters. Thank you for using that lovely terminology. Okay? So I'm going to say there are 1,000 milliliters in a liter. And then you guys can do the math, and that's going to give you molarity. Okay? So far, so good. I'm trying to ease you into this. All right? So now we're going to go harder. Now we're going to go harder. So, we're going to go all out.
Oh.
Okay, here we go. What is the volume of a solution that you need if you have 65 grams of potassium nitrate and you want a 0.5 molar solution, stay with me, okay? So, what am I looking for here, guys? What do I want?
You want molarity?
Volume. I want volume. It doesn't say, but the easiest thing to do here would be liters. So I want liters. If I want a single unit, what do I start
A
with?
single unit.
A single unit, which up here is a single unit.
Grams.
65 grams. So I'm going to write 65G on right now. Nelson, stay with me. You're not going to learn anything from the top of your head facing me. Okay? Now, I remember this capital M really means moles per liter. So I need to get to moles so that I can use that. How do I get to moles? I got to do the shopping list thing. And my nomenclature, right? Potassium nitrate. Potassium is K plus 1. What's nitrate? NO3 minus 1. And so what's potassium nitrate? KNO3. So I just need somebody to add up 3 O's, an N, and a K for me.
On it.
Thank you. So 1 mole of potassium nitrate weighs, while Ty gets that for me,
101.1.
what is it?
101.1.
101.1. All right. That's what she says. I trust that she has done that. And everybody knows how she did that, right? Shopping list of potassium nitrate preoxidation. All right, now is the money step.
I like that.
Here it is. I got rid of grams. I'm in moles. I want to get to liters. Do you see anything else in my problem that I can use? Molarity. Okay? This is moles per liter. How can I put that so I get rid of the moles? You gotta love Paige. She says, well, Mrs. Foy, put the 0.5 M, 0.5 moles on the bottom. And you may be going, where did Paige get that? Where did she get that information? She got it from there, right? She got it from there. She knew that a capital M means moles per liter, and she flipped it. Just like what we used to do with density problems. When we have to make the units cancel, and then I get to liters. So yesterday, I had Dan's brother, who was one of my former students, come in, and he is taking chemistry and he is taking biology at a college in Virginia, a place called Bridgewater. It's very pretty. And he was like, guess what, Mrs. Floyd, we do factor labeling. Oh yes, oh yes. And then I was talking to another one of my former students, Tori Hinkle, who goes to Penn State. Guess what? They do factor labeling, okay? Any science class that you have from this point forward, you can solve problems with factor labeling. It's very important. Oh!